We'll be learning about elasticity in cloud systems. This is from systemsarchitect.io. Like this and subscribe to the playlist and channel. Elasticity is the ability of a system to automatically adjust its resources to match demand. That adjustment runs in both directions. It adds capacity under load and removes it once load falls away. The removing half is what separates elasticity from plain scalability. So, what actually happens differently in an elastic system? An elastic one grows and shrinks on its own, with no one watching a dashboard. A merely scalable system grows when you ask it to. You configure the rules once. The system then keeps matching supply to demand on its own. Elasticity turns capacity from a fixed cost into a variable one, so you stop paying for machines that sit idle overnight or over a quiet weekend. That single shift is often the largest lever you have over a cloud bill. It also protects you from the opposite failure. A sudden spike is one a fixed fleet cannot absorb. Elastic systems apply just as well to a simple app. That app might have just one busy hour a day. They apply just as well to a complex global service. Its demand moves around the planet. Bolting elasticity on later usually means rewriting how the application holds state. Scaling out under load is the easy half, and most engineers design for it instinctively. Scaling back in is the half that actually saves money. It is also the half that is easy to neglect. An auto-scaling group that only ever adds instances is not elastic. It is just slow to grow. Real elasticity needs a scale-in policy with the same care as the scale-out policy. Scale-in protection stops the group from terminating an instance mid-transaction. Connection draining lets in-flight requests finish before that instance disappears. Get both directions right. Capacity then tracks demand as closely on the way down as on the way up. Reactive scaling watches a live metric like average CPU utilization or requests per instance, and target tracking is the simplest form, holding that metric near a number you choose. Scheduled scaling instead sets capacity ahead of time. It works for a known daily or weekly pattern. A retailer might scale a fleet up every weekday morning before traffic actually arrives. Predictive scaling goes further, using historical load to forecast tomorrow's demand curve. It can launch instances minutes before that demand hits. That head start matters because new instances take real time to boot and warm up. Combining all three is the common production pattern. Reactive covers the unexpected. Scheduled or predictive covers the known. Lambda functions are the purest expression of elasticity, scaling from 0 to thousands of concurrent runs while you are billed per invocation and per millisecond. Never for idle capacity. What about containers instead of functions? Fargate applies the same idea to containers. It removes the underlying servers from your management entirely. DynamoDB's on-demand mode scales read and write throughput automatically as traffic changes. Aurora Serverless does the equivalent for a relational database. It adjusts capacity units to match the query load. Each of these hands the scaling decision to the platform. That costs you less direct control over when it happens. For workloads with genuinely unpredictable or spiky demand, that trade-off is usually worth taking. Elastic scale-out only works if any instance can pick up any request, which requires pushing session data out of the instance itself. Sessions move to a shared store like Elasticache or DynamoDB, reachable from every instance. Uploaded files move to object storage like S3, never to local disk. A stateless instance can be created or destroyed at any moment without losing anything. Elasticity amplifies the cost of getting this wrong. A system that scales several times a day cannot afford a single special machine. Design statelessness in from the start, and elasticity becomes almost free to add. Thrashing is rapid, wasteful oscillation between scaling out and back in, and it happens when a metric hovers right at the trigger threshold. Cooldown periods pause further scaling actions for a set time. That gives a new instance time to start absorbing load before it is judged. Choosing a slightly wider target band also reduces how often the threshold gets crossed. So how aggressive should scale out really be? Good policies scale out aggressively because undercapacity costs you customers. Good policies scale in cautiously because over-eager termination costs you reliability. Getting that asymmetry right is what makes an elastic system feel calm instead of jumpy. A single region app with one predictable daily curve needs only a modest auto-scaling group. Time zones wake up and go to sleep. Traffic then gets shifted between regions as one evening quiets down and another morning begins. Each region then runs its own elastic fleet, sized to its own local pattern. Global load balancing routes each user to the region best able to serve them. Route 5.3 and Global Accelerator both do this job. Complex services often combine several elastic layers. A serverless API might sit in front of an elastic database tier. Each layer scales on its own signal. The result is a system that reshapes itself continuously. It never settles around one single capacity plan. Learn more at systemsarchitect.io. Like and subscribe to the channel and playlist. Spot instances add a second axis to elasticity, trading availability for a steep discount, and an auto-scaling group can blend on-demand and spot capacity to cut costs by up to 90% on interruption-tolerant workloads. Savings plans and reserved instances then cover the steady baseline capacity. That baseline runs on committed pricing underneath the elastic layer. Budgets and cost anomaly alerts act as a second guardrail. They catch a runaway scaling loop before it turns into a surprising invoice. Treating cost as a metric you scale against closes the loop. It should not be just a number you review monthly. Cost optimization is the headline benefit, since you pay for capacity only while demand actually needs it. Performance holds steady because new capacity arrives automatically. It shows up before a spike turns into a slowdown. Operations get simpler. Scaling decisions no longer wait on a person watching a graph. Reliability improves too. A failed instance is detected and replaced by the same mechanism that handles growth. Future-proofing follows naturally, since the same policies absorb next year's traffic without a redesign. A workload with genuinely flat, predictable demand gains little from elastic policies and their added complexity. A fixed reserved instance fleet, sized once, can be cheaper and simpler for that case. What's the catch with serverless elasticity? Serverless elasticity brings cold starts. That is a real latency cost for the first request after a period of idleness. Latency-sensitive paths may need a warmed, always-on tier instead. Elastic systems are also genuinely harder to load test. The thing you are testing keeps changing shape mid-test. For those cases, lean towards simpler fixed capacity, or use provisioned concurrency to remove the cold start specifically. Elasticity is the automatic matching of resources to demand in both directions without manual intervention. It turns idle capacity into savings. It turns sudden spikes into a handled event rather than an outage. Apply it by designing for statelessness first, then layer reactive, scheduled, and cost-aware scaling policies on top. Thanks for watching and listening to this, and subscribe to the channel. Find a lot more articles and guides on both systemsarchitect.io and codeguides.io.